Okay, great. Let's get started. Wow, it's so loud. Yeah, today we're going to talk how DA is implemented in Polkadot, kind of to explain how we went through just Azure coding to some optimizations that we have today. The same principles actually will apply to how DA works in GEM, but for this speech, yeah, I'll be talking in the context of Polkadot, so we'll be using the Polkadot terminology for those who are familiar with it. Yeah, my name is Kamil. I'm founder and CEO of a company called Quadrivium. We're the company behind KAGOME, which is the C++ implementation of Polkadot host. It's basically an alternative to Polkadot SDK, which you can use to run validating nodes. Well, we already live on West End. We are testing our node on Kusama and hope to launch on Polkadot really soon. But yeah, to get started, let's maybe first define why we need relay chain. So the Polkadot is really optimized to validate parachains, and validation of parachains really includes two parts. First is proof of execution, which is basically we parachain executed, well, collator submitted some block, we check its validity, we check its state transition, and then, well, we claim that, yeah, state transition is valid. But the second aspect is data availability. It's actually the publishing the data that we need to verify that, well, this parachain block is actually valid. And it doesn't matter like how fast would be our execution engine. I don't know, like you can imagine we have, I don't know, nearly optimal Merkle tree-based parachain with some super parallelized virtual machine. If it has so much, if it submits so much transactions that our data availability layer cannot process, well, basically we'll be limited by this constraint, which is why it's very important to optimize for data availability. Okay, so what's the purpose of DA, really? I would say it's a very little bit different from common rollups perspective, because we have like, well, let's briefly compare like optimistic rollups, validity rollups, and parachains, also called cynical rollups. So in case of optimistic rollups, they really work very similarly to Polkadot in some sense because, well, they submit the data to layer 1 to allow anyone to verify it. And then we have like 7 days period when anyone could check this data, well, basically recreate it, well, run the block and submit fraud proof. It's then, yeah, validity rollups, they actually, I would say even more similar to Polkadot because, well, they also submit proof of execution in the form of validity or ZK proof. And then they also submit the data to layer 1 so that anyone can actually recreate the data that we need to actually verify this proof. But the difference with Polkadot is that this recreation and this validation that, well, this data exists actually done by relay chain validators. In contrast to optimistic or validity rollups, we usually have, well, either light clients or some third-party providers that check that data is indeed available and they also, well, can verify it. In case of Polkadot, it's done by relay chain validators. So we really have to optimize not only for ensuring that the data is there, on relay chain, but also ensuring that, well, we can recreate, recover this data very fast because that's needed for parachains validation. So what we really want to optimize for? First is, well, fast parachain blocks finality. We have 12 seconds within which we have to, well, collectors, they should create block. It should be submitted to our relay chain. It should be validated on relay chain. Then this data for this block should be published. Then we're running additional procedures to, well, again, checking that its data is valid. Well, we can perform state transition. And, well, sometimes we even escalate disputes in case someone, well, doubts that the data is indeed available and, well, we can execute the parachain block correctly. The second thing is, well, we have to really optimize our bandwidth that we use. So, well, targeting more than 300 parachains on Polkadot, well, there will be a lot of traffic, a lot of transactions that we're actually making available. So, yeah, we have to keep in mind how to optimize traffic to use it in the most optimal way. And next thing, of course, is we should have very high level of data availability guarantee. As soon as the parachain block is finalized, we have to be close to 100% sure that, well, the data is available and, well, we can actually execute this parachain block ourselves and check that it's valid. The next is, well, we have to understand like what kind of data we want to make available. First of all, obviously, we have to publish our parachain blocks, which contains a bunch of transactions. And the second thing is so-called witness data. Obviously, relay chain validators, they cannot have the state of every single parachain. What we do instead is, well, parachains, well, the collators, they, in addition to parachain blocks, they also submit so-called witness data, which is basically the subset or sub3 corresponding to the set of, well, to the state of the parachain. And this data is actually enough for us to execute transactions, and well, it also should be made available. There is also some metadata, and all of that information that we're making available, we can call it proof of validity that we actually trying to publish. Yeah, next, to understand how we can improve data availability, we have to very briefly touch on how parachains protocol works in relay chain. So we start with backing procedure where we basically split our relay chain validators into groups. So each group is assigned to some parachain. Well, in the past we could say that there is one-to-one relation, so that each parachain is validated by single group or single core. But with elastic scaling, that's not the case. So we can have actually a single parachain assigned to multiple cores, so they validated by multiple backing groups. And what we do is we really randomly create these groups, and each group validates its core, its parachain block, and they claim either this block state transition valid or not valid. If it's valid, then it's tasked for backing validators to actually publish the data so that anyone now verify that, well, state transition could be done and checked. The naive approach would be just distribute the proof of validity to every single relay chain. So you remember, as I said in the previous slides, that, well, we have the relay chain validators are responsible for checking data for validity and ensuring that state transition is right. So naive approach would be just send this proof of validity, this entire replica of data to every single relay chain validator. And well, I'm saying this naive approach, but actually many data availability chains or the solutions, they actually still use this approach so that they kind of, every validator has its own replica of the entire data. But we can optimize it. Instead, what we can do is we take this POV data, then we apply erasure coding. After we did erasure coding, this data kind of gets larger. Well, for example, we had data of size n, then it gets size 3n plus 1. And the cool thing about erasure coding is that after we did it, we split data into 3n plus 1 chunks and distributed to 3n plus 1 validators. So each of validator has its unique chunk, but none of validators has the entire data. So that way we can scale the network because none of the relation validators has to actually store the entire replica of POV data, which could be large. In order for us to understand how erasure coding works internally, because that's important for some optimizations that we're actually doing in Polkadot, we introduce very little math. So what we really do is, well, we take our data. For this example, we just consider very small data of size of 4, and we operate in finite field of size 97, but in general, we obviously work with much larger data of the order of multiple 100 kilobytes. Finite field is also much larger, has much larger size. So our task here is to go from this. Well, we take this data and then we try to find corresponding polynomial for this data. There is a cool property of polynomials is that, well, if we take any n plus 1 coordinates, they uniquely identify degree n polynomial. So what it means, so what we can do is we take this data and we transform it into evaluation representation of polynomials. So basically the chunk index is x and the chunk value is f of x. And going from this, we can calculate our polynomial. And the cool thing is that this polynomial, f of x, that we calculate, no matter which 4 coordinates we take from this graph, actually we will always end up with the same polynomial. And how do we use it? We take this polynomial and then we kind of evaluate it at more points. So we had just n evaluations in the beginning, And now we have 2n+1 more evaluations. And these basically our data availability chunks that we distribute. Any n of these chunks actually enough for us to reconstruct the data. Because as I said, yeah, we have a property where we can take any n coordinates, or just 4 in this case, and recreate this polynomial, and we will always end up with this polynomial. I should say that it is very costly mathematical operation, so we usually use either univariate Lagrange interpolation or fast Fourier transform, and we actually want to avoid doing that as much as possible. I mean, reconstructing this polynomial. Yes. What else do we do? So, what actually goes to our block? On top of this erasure-coded data, we construct Merkle tree, and the Merkle root of this tree actually is getting submitted to the next relay chain block. And how we use it? So we do chunks distribution. So baking validators, as soon as they erasure-coded the data, they send chunks to each of the validators. And in addition to chunks, they also submit Merkle proofs that, well, this chunk, it actually corresponds to the data availability root that is attached to the relay chain block. Another thing that goes to block is actually signed bit fields. As soon as validator receives its chunk corresponding to some parachain, it sends the statement saying that, hey guys, I have this chunk corresponding for this parachain. And then the next block producer will kind of collect all of this information in the form of signed bit fields. And that way we can actually calculate like, hey, for example, here we see that validator 1 has chunk for parachain 1, for parachain 2, but it doesn't have chunk for parachain 3, and so on. And then we can calculate like, okay, we have enough chunks to actually recreate the data, so we can consider this parachain block as included. However, it's important to notice that, well, inclusion doesn't necessarily guarantee that actually the data is available. That's just the claim that some relay chain validator is claiming that, well, he has the chunk for this parachain block. But in reality, he could lie, and we should check him. And another thing that could go wrong is that, well, the baking validator who was performing the erasure coding, he could be lazy and not really do erasure coding, just attach some random data to extend the original data and construct wrong data availability root, or he could hide or corrupt the original data. And unfortunately, we have no other way to check that the data actually corresponds to parachain. We have no way but just recreate this data and reconstructing the Merkle tree. And that's why we have the approval stage of validation for parachain blocks, where basically we randomly assign additional group of validators to reconstruct the data and then execute the block. And here I hope you now understand that the reconstruction should be very fast in order for us to have very high, basically, parachain blocks throughput. So how does the reconstruction work? So I already said to you that like we can get any n out of 3 n+1 chunks to reconstruct our original data. So for example, here we have, for example, some validator that is participating in approval validation. Well, it selected some random, it fetched some 4 chunks. The original data was also of size 4. And then it reconstructs the polynomial. As I said, we will always end up with the same polynomial. And then this polynomial is getting evaluated at the first n points. In our case, it's just first 4 points. And this is actually our original data. So we just concatenate these chunks. And here we are, we have the data that we're validating. As I said, like it's very costly operation to actually calculate this polynomial. And yeah, we want to get rid of this step. It is so costly, yeah, that we first in KAGOME we tried to optimize this step as much as possible. So we didn't just take the original implementation in Rust and just created some bindings, but we actually implemented our own native implementation in C++ to get as much performance as possible. Our implementation is actually faster than original implementation in Rust, and we are using this now. And but as I said, like this optimization, we want this not to be really important. So because we don't really want to run this math where we calculate our polynomial. So we want to get rid of this as much as possible. Yeah, and should we briefly mention the just final step. In case someone is not able to reconstruct the data or he claims that state transition is not right, well, then we escalate disputes where every relay chain validator is actually now trying to reconstruct data from these chunks and then, run validation procedure. So let's talk about optimization that we can do here. The most obvious one is, we have you remember we have these backing groups of validators that executed the parachain block. And since they executed it, so they have the entire data already. So we actually don't need to go to reconstructing this data from chunks. Maybe we can just go to these backing validators because they already have all the necessary data. They had the parachain block and this witness data. We just go to them and request it. And that's actually what we do in Polkadot SDK and in KAGOME. But with one caveat, only when the data is less than 128 kilobytes, because, if validators that participate in approval validation, they actually go to the same backing group validators. These validators from backing group, they would experience a lot of traffic, and that's not very optimal for bandwidth, so response could be delayed, and that's not fast. So if the data is larger than 128 kilobytes, instead of just requesting this data from backing validators, we actually reconstruct it from chunks. But luckily, we can optimize this step as well, because our chunks, they are systematic, meaning that first n chunks actually correspond to our original data, meaning that, we can have if we requested just first n chunks instead of requesting just some random n chunks, then we can just concatenate them and get our original data without the need to running through this step where we calculate the polynomial. As I said, it's very expensive. And that also works. However, another, again, kind of similar problem that we could face is that, if we always request chunks from validators who have first n chunks, they would experience constant pressure, a lot of traffic, a lot of congestion, which we really want to get rid of. So what we do, that actually was proposed in RFC 47 by one of the parity developers, is we're introducing chunk rotation, where we don't just, always have the situation where first n relay chain validators, they have first n chunks. Actually, it also depends on the core index, so that we have, for example, for core index 0, it's one-to-one matching between validator index and chunk index. In case of core index 1, the chunk index 0 stored by validator by index 4. So we have this shift by 4 because we have basically our original data has size 4. That's kind of how chunk rotation works. And it really allows us to distribute the load in the system, the traffic that we have among all validators, not only constantly asking chunks from the first n validators. And that's actually it, long story short, when the data availability in Polkadot went through multiple optimizations over the past few years. So in the beginning, we just were reconstructing the data from erasure-coded chunks. Then we noticed that, we can actually fetch the full data already from the backing validators. But then we noticed some problems there, and then we introduced the systematic chunks with chunks rotation. And that's what we have today. And I believe actually chunk rotation, it probably is not introduced yet in Polkadot, but at least the code is there and it's ready. There are some zombie-net tests, and we have it implemented in KAGOME. And in Gem, we also can take advantage of systematic chunks because we will also use the erasure coding scheme that allows that. And I think that's it. Thank you. Yeah.
Awesome, thank you. Thank you very much. Do we have any questions for Kamil before we let him go? Some big questions about DA. Okay, fine.
Okay, fine, thanks.
Thank you very much, Kamil.